They provide the basic backbone of traditional NLP. So those things we will cover. We'll talk about some ways of representing words and documents from statistical cues. We have already started discussing about that. So singular value decomposition is one such technique. And then today we'll talk about one more technique like that. We'll also talk about in-gram language modeling and smoothing techniques. Then we talk about understanding the language structure. So we will see that, okay, whenever we have an input text, which is a natural language text, so we can, different words depend on each other in many different ways. So understanding the structure of dependencies among terms and phrases with themselves will be the next topic. Parsing. There are different types of parsing. Those we will go through. Then whatever we're talking about representing words, we'll elaborate that a bit, contextual and non-contextual representations. And topic 1 and topic 3 may go on in an interlaced way. It may not be exactly sequential in that nature. Now, in NLP, we talk about 3 basic things. One is syntax, the second one is semantics, and the third one is pragmatics. So the parsing and various other kind of sequence labeling things, like the ones that Srijit was covering and he'll cover in his next lecture. So they come under the syntax part, and then semantics will try to understand the meaning, and many of the representations which we are talking about try to capture that semantics. However, there is another level which is pragmatics, which essentially talks about, the overall, if there are multiple sentences, if there is a big piece of a document or so on, so how, the meaning is there embedded, it flows from, one part of the document to another, and what is the final thing, the concept or idea that it tries to give. So these are actually at the higher level of language understanding, which is pragmatic. So there we'll talk about co-reference resolution, we'll talk about discourse and so on. We'll also cover deep learning for NLP. Now, having said that, for many of the techniques, for many of the approaches for the 4 topics which you have mentioned earlier, we may also look at deep learning based techniques. So this again may not be taken up as a separate topic, but may flow through the discussion at many points. So we'll talk about sequence to sequence models, and we'll also talk about advanced language models. Then NLP, as it is becoming more and more applied nowadays, so we'll look at some very specific applied topics in NLP, which are major research topics in themselves. So dialogue systems and machine translations are 2 examples that we have included here, but instead of this, we may cover some other things also. So overall, this is the structure that we are going to follow. And coming to the lectures, so far you'll see that in the timetable, maybe only 4 or 5 lectures we have marked. So by the end of next week, we hope to populate the lecture schedule for this entire semester, and also the exam date. For exam date, we actually need to talk to the other instructors also, so that we can have a common date or common date for holding all the exams. So this is something that I wanted to convey before we proceed to the
did we cover when we are going to get the assignments and these quizzes and all?
Quizzes, most likely quizzes will be surprise quizzes. My quizzes will be surprise quizzes, and assignments also. Once we cover some part of the lecture, we will give an assignment. So depending on how much we can cover today, there might be an assignment which will be posted this week. Now, good that you mentioned this. I hope a good number of people have also joined. So for each assignment, we'll have a group of 2. So two of you can pair up, and yeah, you can work on the assignment together. So this one will circulate a Google form where you will be asked to provide your team composition. So yeah, start talking to your batchmates, form the teams, and yeah, the assignment statement as well as the group formation Google form we'll share maybe within the next 3-4 days.
Okay, sir. Thank you.
Okay. All right. So let us now move on. So if you remember in the last class, we were talking about learning representation of words. So initially we started with learning representation of the documents. And then we saw that since documents are nothing but composition of words, specific composition of words. So if we understand the meaning of the different words, then from there we can actually infer the meaning of the overall document. Or if you look at the entire document, if you identify different parts of the document, it may mean different things. So if we have the representations of the words, it can also help us in understanding meanings which are in the parts of different documents. Sorry, in the different parts of document. So with that, we talked about the singular value decomposition, where our starting point is a term document in this incidence matrix. And from there, we do singular value decomposition, then truncated SVD and so on, so that we can get compact, dense vector representations for the documents as well as the terms. Now we saw that, okay, this is meaningful representation and so on. However, SVD has some drawbacks, like you need to process that entire term document matrix together, right? So if we simply assume that, okay, there is some method SVD will do, which will do all the tasks for us, but there also the major consideration becomes it operates on that entire matrix. Now for any real collection, the matrix can be really large. So that is one problem. And then if we add new document, if we add new term, how is that going to impact the entire processing? Can we handle that incrementally and so on? So these concerns also remain. And then there is a linear algebra based technique. So there are many optimized linear algebra routines which can be used, but still there is a limit to which they can perform. So people they were on the lookout for other methods also. Some of those methods will come to, but if we know that the document collection is static, it's reasonable. This still provides a very good way of representing the words and documents. Okay, now we'll talk about one technique which was mainly brought in to understand the different concepts which are there in the collection. So this term document index matrix is built from a document collection, right? Now, if somebody asks, okay, I have a large collection, and then what are the different things which are being discussed in this entire collection? Now, this may become very handy uh, in scenario. Suppose in your organization you have a collection of many feature requests or change requests, and then somehow at a high level wants to know, what are the different things that people want. Now from that entire collection can we infer the different things. Now this method is known as topic modeling, or understanding the topics which are present in the collection. However, as we go on with the discussion on this, we'll see that even here the method, although the purpose was to identify the topics which are being discussed about in the document, will get words and document representations. In fact, there are many uh, many works where people use LDA or use some kind of topic modeling, and then take the vectors or which vectors corresponding to the documents or the words, so that
Can
that
you
you
define
down.
that, sir, can you define the topic modeling again? Just the previous two lines.
Yeah, I'll talk about that. So thing is, you have a large document collection which can be say 100,000, 10,000, whatever size. Now each document essentially talks about certain things, right? So if you download a collection from Wikipedia, which is on say Indian athletes, okay, so possibly it will talk about some track and field related sports and the athletes were present there. Then maybe some team games. Then it may also talk about some games which are of the nature, I mean, like cricket, football, and so on. You can also talk about tennis, badminton, things like that. Now, all this collection is with you, and then suppose we want to segregate them into different topics. Now, you can consider this to be some kind of clustering. So, yeah, we're trying to identify different groupings. Another example could be like the example that I gave just before is that the different change requests or feature requests which come in an organization, or maybe the complaints which come in an organization. So if we talk about the complaints, we'll see that for an online service, sometimes we'll see that, okay, people will say service is slow. Sometimes people will say that, okay, certain pages or certain things do not work well. There may be also the situation that where people are having access issues and so on. So at a high level, when we try to give a judgment on, or we try to get an understanding or comment on what all different things we might be talking about, these points come to us automatically. Maybe these are the very first points that anybody would mention. However, suppose the organization wants to know from this entire collection of complaints, what are the different topics that people talk about? So is there a way in which automatically we can identify this? Now, after we automatically do this grouping, we may see that, yes, we are getting something which is about uh, access issues. There may be something which talk about, the application breaking after the recent update and things like that. However, there could be some other topics, there could be some other themes that we didn't anticipate at the beginning, but when we go through this processing, that automatically comes up. So this is where topic modeling can help, and this is what topic modeling is. Abhinav, does that answer your question?
Yeah. So does that topic extracted will be unigram or it can be n-gram topic?
Both options are there. There are different techniques. Yeah.
Okay, thanks.
Yeah. So, right. So let us talk about topic modeling now. So as I just mentioned, and you may have understood from the discussion also, so these topics are something like clusters. And as we know, in case of clusters, the clusters typically do not have names, right? We just know, okay, there is one cluster, there is another cluster, there is another cluster. Now, if we want to assign a name to the cluster, that will be a different technique. So here also these 2 points we will share with the regular clustering. Topic only is one kind of clustering only. So firstly, we'll identify the groupings. Secondly, for each grouping, we'll not have any name, but one can actually look at the cluster and then understand what could be a name for it. Okay, so there are techniques for topic modeling, and one of those is LDA. Now, LDA means latent dirichlet allocation. So this is one specific algorithm that we are talking about. So if you see the machine learning literature, there is one more LDA, which is the linear discriminant analysis.
Hello?
Yeah.
Sir, mention the name one more time. What is the LD?
It's latent dirichlet analysis. It will be there in one of the subsequent slides, I guess. It will be there. So here it is built on the notion of topics. So so here it is like and some examples of topics I just gave, and there are many topics. Now each document is actually a mixture of topics. So if we talk about medical kind of scenario, so we'll possibly see that, okay, there are some documents which talk about asthma, there are some documents which are talking about arthritis and so on. However, there can be scenarios where one document talks about multiple topics. In fact, that's what typically happens. Even in the customer care scenario also, what we talked about, a single complaint may be connected with access issue as well as performance, right? So documents are typically mixture of topics. Now, when a document is a mixture of multiple topics, each topic is not typically will not be there in equal proportion. Right? So if there is a document which talks about 3 different topics, some topic might be present there more, some topic might be less, some topic might be even lesser. So the proportion of the topics being present in the document will not be uniform. See, across documents, these proportions will be different, and inside a document also for all the topics the distribution may be different, and these topics themselves are unknown or latent. Okay, so nobody told us that okay, these are the topics that we are trying to find. So here the first 4 bullet points, if you look at, so this identifies the problem setup. Okay, now if we go further, what we want to utilize is that a document is a collection of words that we all know, and which words are present that depends on the topics of the document. Now we are trying to go to the solutions. So which words are present in a document depends on the topics there. So if I am trying to talk about I'm trying to create a document which is on science, there will be some words which are more probable in that document. On the other hand, some words might not be there in this document. So what topics are there in the document, they influence the presence of the words which are present, which are there in the document. Now if you just reverse this, okay, what words are present in the document, from that we can infer the topics. Now essentially these things are connected mathematically in that formulation. So finally we need a mechanism to identify the topics. That was the goal we started with. Then connect words with topics. So which is connected with this bullet where we say that okay, words, which words are present depends on the topic. So we need to connect words with topics, and we also should be able to explain the document with these learnings. Okay. So that means for this entire document, can we get the topic vector? Which topic is present in what proportion? Now, if each topic is considered to be a cluster, you can very easily see that okay, this is now a soft clustering that we are doing. So for a document, we can say that okay, it belongs to the first topic 80%, the second topic 5%, and the third topic 15%. Right? So we are not saying each document will go to exactly one cluster, no more, no less, but it can be spread across different clusters. So in that way, it is soft clustering. On the other hand, are you familiar with any hard clustering algorithms? The question is, you may have gone through or you might be aware of different clustering techniques, and we say that you know, this topic modeling is a soft clustering.
The K-means is a hard clustering.
K-means is a hard clustering. Any other clustering techniques that you are aware of which is hard clustering?
Scan.
Sorry,
DB scan.
DB scan. Yes, DB scan can be one more hard clustering. All right. So there can be scenarios where hard clustering is preferred. There can be scenarios where soft clustering is preferred. So right. Fine. Now let us try to look at the some kind of so we now want to go to the solution, right? Now to motivate the solution steps, we try to see that how is the document generated. So idea here is that we said that a document will be a mixture of topics, which we can see from this. I mean, this shows that. So there are many topics, out of which these 3 topics are more contained in this document, and for there are many different topics, and for each topic there is a word distribution. Right? So as when we say that okay, if I'm trying to create a document about sports, then some words will be more probable and some words will be less probable. Okay? Similarly, for each topic there is a probability distribution over the words in the vocabulary. So this is called word topic vector, and this is typically called a document topic vector. So now let us assume that we are having to generate a document with some topic distribution in mind. So what will be our steps? So this is an approach where we say that we know, let me see if I can turn on the pen and write here. Suppose somebody has told us that the document's topic distribution is 0.8, 0.05, 0.15. There are 3 topics only. So before generating the first word, so it assumes that the documents are being generated word by word. When all these parameters are given, let me call this vector as theta. So I'll generate the first word. So for this, I'll first pick a topic from here according to this distribution. So suppose I, depending on these probabilities, I pick topic 2. Okay, then I know that I'm going to generate a word for topic 2. Now I go to these vectors. No? So this is beta 0 for topic 0, beta 1, that is the vector for topic 1, beta 2 is for topic 2, beta 3 is for topic 3, and let us assume that there is a 4th dimension also, which is 0. There are 4 topics. So I know that for the first word I have selected topic 1, which is this one. Now I go to the beta 1 vector where we have the probability distribution over words for topic 1. So among them I pick one vector, one word randomly. Suppose I call it W1. Then my first word is generated. Now for the second word, again I select a topic based on this. We assume that there are 4 numbers that I can possibly generate along according to these probabilities, and I generate the first topic. So now I'll go to the word topic vector for topic 0, which is beta 0, and based on these probabilities I'll sample a word from there.
So you will be selecting a word based on the probability distribution of the word topic vector, right?
Right.
Yeah, so it will be multiplication of both the things, so document topic vector and the word topic vector.
Yes.
To generate each of the words.
Right. Overall probability we try to
And are we assuming the probability of selecting words equally likely?
No. So if you see the numbers here, they're different. Right?
Okay.
So then for this, suppose I pick another word. Now this is W2. So I repeat this process. Till I generate, the either stop token, or I generate a fixed length that I have in mind, and things like that. So there are 2 steps. The document generative process has 2 steps, or 3 steps rather. Let me see if this is documented in the next slide. No. Step 1, get the topic vector for the document. Get the topic vector for the document, which is theta, but it will be vary for different documents. So I am writing theta d. So for document 1 it is theta 1, for document 2 it is theta 2, and so on. Then from theta, now suppose our document has n words. So I'll have for I equal to 1 to 10. Firstly, I'll select a topic, let me call it Z, from theta d. And then in step 2.2, we'll generate a word. So I'll write it as Zi, because for ith y the topic is Zi, and the word itself is Wi, which I'll generate by looking at beta, right? Beta Zi. So this is the step. I keep repeating this till the time I have generated all required number of words. Yes. Is there
Can you explain the point number 3 and 4 again? This one from Z basically. Yeah, this one.
okay. So for each word, firstly we sample a topic, and this topic sampling happens from this theta.
Yeah.
Okay. Now once we know that okay, I am for this position, the topic is Zi. Now I try to generate a word which is more aligned to that topic. So I go to beta for that Zi. So like this, and from here we generate a word by following this distribution. So this Wi is being sampled from beta Zi.
Okay. And for basically the other for I is equal to 1 to n are we are sampling over the words there. N are the words for in that document, right?
Right. So this 2.1 and 2.2 are inside the for loop. So these two steps repeat as we go from word 1, word 2, word 3, like that.
So the WI is generated by looking into the topic words, right?
Yes. Yes, it's from here.
So basically that Zi in the Zi we are actually identifying which theta do we need to go to, and based on that theta we are going to the corresponding beta there, right?
Yeah, which component of theta?
Yeah, which component of theta?
Okay. Now, can you tell that theta is this one, and we are generating one topic from here. So what kind of distribution are we talking about here? We have n different choices. We are picking one of them. What distribution?
Binomial.
Close but not exact. So binomial, this binomial.
I think
Is
It's a multinomial.
it gonna be
multinomial.
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 This extension of binomial to more than two outputs. Similarly, from this beta, so this is sampling from a multinomial distribution, and this sampling is also from a multinomial distribution. So there are these different choices. We are picking one of them, and yeah, these are kind of yeah. So each of them has a probability associated with it. Okay, so if you look at other references for LDA, sometimes people will use these terms. Sample Zi from this multinomial distribution, or sample Wi from multinomial distribution. Now, finally, when we look at this entire generated document, please note that these WIs are the only observed things. So when we have the corpus, we know what the WIs are, but we do not know what this theta is. We do not know what this Z is. We do not know what this beta is. Right? Now here, actually, we'll then reverse the process when we learn in the learning principle. So here, from these observed, we'll try to identify this beta, Z, and theta. Okay, and only assumption is that, like we do in k-means, we know, or we need to specify the number of dimensions of this vector, which is the number of topics which I expect in the vectors, expect in the collection. Now, all right. Now, one thing is that we do not generate the documents. We do not try to generate the documents following these steps. We assume in our mind that this is the we assume in our mind that this is the process in which it is generated, and then we try to reverse this, and based on the observation we try to predict these observed things. So in your machine learning, let me see if there is a reference we
So,
have.
so is this related to multinomial mixture model?
Uh, Related, yes, but here more to,
Later model, right?
there are more to it as we have these additional.
Yes, yes. Their parameters have increased.
Correct, correct. So now I think so. If there is any query at this point, you can ask, because the next step we'll talk about some inferencing part.
So one more query here. So what if there are subtopics inside the topics? Then is there any approach, or we will include one more parameter here called the subtopics?
So here we are talking about, I mean, you have rightly pointed out and rightly observed that we are talking about a flat hierarchy and here, but there is hierarchical LDA where we can actually go deeper and identify subtopics as well.
Okay.
So in many of the machine learning topics, where suppose we have a tabular data feature information is there for each example, and you may have seen that we do something like maximum likelihood estimate, right? So there we say that very simple. Suppose we don't have to think about very detailed process, but suppose we have a list of numbers which we assume has come from some normal distribution, and we want to identify the parameters of the normal distribution that has generated this data. Okay, so in normal distribution, what parameters do we have?
Mean and standard deviation.
Okay.
Can you just repeat that part? Like, why are you considering this should be a part of normal distribution?
So it has been observed over a long period of time in the real world. Many observations that we have that tend to follow normal distribution, say height of people, age, and many other things. So that's the assumption that we are making. We can actually talk about many other distributions also. We can say that okay, we have a data and it has come from some other distribution, but the parameters will be different. But that's simply an assumption. Okay, so mean, and then suppose sigma square. What is sigma square?
Variance.
Variance. So you may have seen ways, or you may be able to do it if you know the process, our family with the process, that based on this data, if we want to identify this mu and sigma square of the distribution, which we do not know, which distribution actually generated this, we only have the observations. Now there is a way in which we can find this mu and sigma square, right? So the maximum likelihood estimate, we call it. So suppose we assume okay, there is some mu and some sigma square, then we identify if that is the case, what is the probability that we observe this one. So probability of observing x1, or let me write xi, given some mu and sigma square. We know that what is this probability based on normal distribution formula, and then we have observed x1, we have observed x2, x3, x4, xn. So the probability of observing this entire data set, how can we express that? What is the probability that we have observed this entire data set? So in this data set, there are n examples. So observing the entire data set means we have observed example 1, and we have observed example 2, and we have observed example 3 till we have observed example n. So that means all these probabilities we need to product them, take the product of them. So pi over this. Now then we want to identify the parameters that maximize this observation probability of this data set, right? Now this thing we then solve for mu and sigma square because they become our parameters. So these are the unknowns for which we want to find the values so that this quantity is optimized. Our optimization function is f, which is nothing but this product. It has two parameters, mu and sigma square, and find that. So there are I mean, simply, this is a very simple example where we can do first derivative, second derivative. First derivative can equate to 0. Second derivative, we check whether it's maxima and minima, and it will be maxima. Actually, we are maximizing the likelihood also. It fits well, and then based on that we can do some calculation to see. Finally, mu will be the average of these, and sigma square will be the from the sample whatever we can guess the variance. Even that will be there. So I brought this analogy because here also we'll be doing the same thing. We have our observation as this WI sequence, which actually give us the different documents. And from this, we will try to understand the parameters which we believe have generated the collection, but we do not know what they are. Very similar to this setup. So the next part next slide will give you the actual diagram and this one. So here I think there is some. No, I think no, this is okay. So theta d. So for each document, we are actually identifying a theta d vector. So which documents gets what vector we do not know, right? So we are assuming that for each document we'll sample a probability distribution. So this theta is not given. So this is sampled from a distribution. So and then once we have sampled the topic, what we do is for the dth document and nth word, we sample a topic, right? So this is what we did in step 2.1. Now we have sampled a topic. From that we want to generate a word from here. Now for that we need this table. So where does it come from? It actually comes from this. So for each topic we have a vector of probabilities associated with different words. So like this is for one topic, this is for another topic, and so on. And what word is generated is actually dependent on the topic that you have selected and this distribution. So these two things together give us the observed word. Now this ZD, this is a multinomial distribution, sampling from multinomial distribution. This WDN, we have seen that this is also sampling from multinomial distribution. However, this theta D, right? We said that for a given document, what should be our theta D? We don't know. So there also we are assuming some distribution from which we sample a vector. Now one point to note here is that this theta is a probability vector, right? And this beta is also a probability vector. So we need to have a distribution for which the output can be a probability vector, which can so where we can assume that there is a collection of infinite number of probability vectors, and this method will be giving us one single probability vector. So that means this process on getting theta d and getting beta k. So these are sampling of probability vectors, and as we know, to sample real numbers we have different distributions like uniform distribution, there can be exponential distribution, Gaussian distribution, and so on. Similarly, for sampling probability vectors, one very commonly used distribution is Dirichlet distribution or Dirichlet distribution. So let me write down here.
So the number of topics in a document is not fixed, or we are also taking a distribution of that.
That we are assuming and providing to the algorithm. So based on that, this decides how many fields will be there in that vector. So Dirichlet distribution is something like, it's a function. Okay, you give it some parameter, some alpha, which is a vector, and it will return you some probability vector theta. Okay, just like in case of normal distribution, you provide mean and variance or standard deviation, it will give you some real number similar to that. Now there are two cases where we need these probability vectors. One is in theta d, another is in beta k. So as we know, and as we see here, even for this distribution there is some parameter to be there. So these are the parameters. For getting theta d, the parameter is alpha. For getting beta k, the parameter is eta. So actually we would not call them parameters, but they will be hyperparameters, because based on this, these parameters come, which actually these are the main parameters which govern the generating process, and these parameters are generated by keeping in mind some other fixed constant here. So these are the hyperparameters. So what you see here is that alpha and n are the hyperparameters. Here, this and this. Theta, z and beta are the model parameters. So theta, z and beta. And theta is the topic distribution in the current document. We have seen that. Z is the per topic word assignment. Sorry, Z is the Z is the topic document per word, and beta is per topic word distribution. So I believe the symbols here are clear, and the meanings of these arrows, those are also clear. Two things we have not talked about. What is this k? So this k means there are k topics and there are k such circles, k such beta values. This d means there are capital D number of documents, and that means there are d number of these theta vectors. This n, which is inside this d plate, means that inside a document D there are n number of words, and for each words we have Z and W. So this shaded thing means it is observed and everything else is unobserved. Hyperparameters we need to specify, but the model will give us the values of theta d, zdn and beta k. So any topic modeling algorithm, if you see, so it needs only one thing as an input, this W, and it will output this theta t and beta k. Remember this zdn, typically it is not output. So it's actually very large, it will be. So it is not output. So at the end of the algorithm, it will return the learned parameters theta d, which is the topic distribution of each document. Okay. Now topic distribution of each document can also give you a representation of the vector, a representation of the document. So LDA can actually give us a document representation also from the topics perspective. And this
Sir,
beta k
is ZDN actually, like Z value? What is Z actually?
So this step, do you remember?
Yeah, but that is the assignment step, right?
Right. Now this for document D, for word I, what was the topic? So this generative process generated some topic for this document and this word. So this is this ZDN, which is generated, not observed.
But it is not a probability value, right? Or is it?
It is not a probability value. It could be like, so it's a topic. So it can say that topic 1, Zi can be 1, 0, 1, 2, 3, one of these 4. So it's a multinomial distribution where there are 4 possibilities, 0, 1, 2, 3, and zeta is one of them. It can be 0, it can be 1, it can be 2, or it can be 3. Not a probability. But this theta is a probability. This theta is a probability, and this beta.
But sir, Zi would also be, isn't Zi would be like for basically this word belongs to this topic, because it is like word, it is a talk. Z is nothing but the per assignment per word, right? In a way.
There is a topic assignment per word.
Topic assignment, yeah. So basically, in that case, for each topic, the probability it would belong to this, that word belongs to this topic.
No, it's Okay, I think there is a subtle variation here. So we won't say that these words belong, this position belongs to this topic. So I equal to 1 to n, this 1 to n are the different positions. So the first position belongs to topic, say 0. And for topic 0, we generate the word, say how. Okay, so in this generation process, suppose we let us write them. So zi and wi. So we start with some theta vector, which can be something like 0.8, 0.05, 0.15. So what is the first topic? So position, and these are the positions or offsets in the document. Say I equal to position 1, 2, 3, 4, 5, 6, and so on. First position, sample a topic, say topic 0. Generate a word, say I. For second position, generate a topic. Suppose now I generate 3. And this for this topic, generate a word, say on this play. Now for the third position, we generate a topic. Now for that, suppose the zi becomes topic 2. So now suppose this is, for this topic we generate a word. Suppose we generate tennis. Then for topic 3, sorry, for position 3, again we generate a topic. Now suppose we talk about, here it comes, sample topic is 0. Now for topic 0, I generate a word. Suppose it says poorly. And like that. Now is it clear now? So zeta is, if you look at for a document, this will be a sequence of this topic numbers, and wi will be a sequence of the actual observations of words.
So the total the iteration will be the, I mean, total length of the theta, right?
Total iteration will be total length of the document.
Total length of the document. Okay.
Yes. Number of tokens in the document.
Sir, will the final generation semantically make sense?
So, so this is the one that we are not generating this. We are never generating this. Just like when we talked about this data set, we did not generate this. We observed this. This is, suppose, the heights which are there. Height of students in a class. We didn't generate these heights. These came as observation, but we assume that these heights are generated by some hidden process, and we are trying to identify the parameters of that hidden process. Here also we did not generate all these. This is given to us, this is the observation, and we are trying to characterize, understand the parameters of this hidden process, which we believe has generated this one. Does it answer?
Got it, sir. Yeah, yes, makes sense. Thank you.
Okay, now the problem is how these are how these values are found out. Now this exact thing will not cover. This requires the understanding of a few sampling techniques and estimation techniques. So at a high level, so this is done by using Gibbs sampling. Gibbs sampling. So there actually we try to fix, you try to vary one parameter by fixing all other parameters. Each step there are multiple sampling happens, then we discard some, we retain some. There is a detailed process which goes along. So that entire process will not cover, but the overall purpose, understanding of this generative process, and that we intend to cover here. And this diagram is a repeat of this diagram. And in this case also we try to identify the we say that the likelihood function, right? The likelihood function we're trying to observe, optimize. So what is the likelihood function here? The likelihood function here is that what is the probability that this entire corpus is generated by following this generative process. Now that probability can be written as P beta theta zw. Okay, so beta theta zw, and you can see that okay, this entire thing can be written as a probability here. So firstly, if you look at I'm not sure whether you went through the concepts of probabilistic graphical models and so on. So there's actually from the probabilistic graphical model, this formulation will be there will be one term for each node, and for each node the probability will be dependent on the incoming arrows. So here this theta these betas are determined by this etas, right? So probability of beta I given n, probability of observing beta I, and this beta I is over I equal to 1 to k number of topics. Now this is one thing which is done, and then we come to this part. So here what happens, firstly given some hyperparameter, we'll generate the topic vector for each document. So that means for each document d equal to 1 to d, we'll have a product here. Then once we have found the topic vector for a document, we follow the generation process where we first from the theta generate a z, the topic value for that document and offset or position pair. Now probability that that exact topic was generated multiplied by, given that topic, go to that topic vector, and now this word is generated. So this probability. So these two probabilities will multiply together. I think that was one question which came. And these two multiplications for each position, and we have n equal to 1 to capital N positions in the document. So this is the entire likelihood function. You can see that it's very complex, and it's analytically by doing, taking the first derivative, setting it to 0 and all that, it's not possible. So that's why the sampling based techniques for parameter estimation is there. So that's about the likelihood function, and just this is the Dirichlet distribution. So given a hyperparameter, which is parameter to the probability distribution, how do we come to this theta vector? So here this is actually given by this function where gamma, we see gamma function and so on. And I've given a sample Python code here. You can, I'll share the slides with you, and you can run it also. So f is the function that returns the probability values, and it takes 3 parameters. So actually we see one parameter here, alpha, but alpha is a vector. So we have just listed each component here separately in this user defined function. So here we are assuming that 3 we are trying to get a probability vector of size 3. So theta 1, theta 2, theta 3, and then this Dirichlet function is called with this, and 5 means we want 5 observations. Okay, so len s is equal to 5. If we print this, we'll be printing 5 different vectors, each of which is a probability. Now typically what people try to do is people set this theta 1, theta 2, theta 3, everything to 1 by k, which means each field in the probability vector is equally important, which means each topic is equally important. However, if you have some numbers small, some numbers large, so that will actually help the model in focusing more on those dimensions. So those probabilities will be higher. So this is, here are some other pointers. So if you want to know what Dirichlet distribution is, you can see in these things. And then this is another additional reference for maximum likelihood estimate. Yeah. So if there are any questions, you can let me know. Otherwise, we have reached the end of the discussion on LDA topic modeling. Remember one thing, if you have a document collection, you pass it to LDA, it will output 2 different things. One is the theta vector. That means for each document, we get a vector. for each document we get a vector, k-dimensional vector, and also for each topic
We get the word vector.
Yeah, so here this will be a, let me erase this part, I think. So if this is the collection you give to LDA, I'll say that we get two different matrices. The first matrix is where for each document we have the topic distribution there, and then for each topic you have a distribution over the different words. So this is typically called a doc topic. Yeah, I should have included it in the slide itself. And this is called word topic. So additionally, what you can see is that, so if your T is say some 10, 20, 100, whatever, so for each document you are getting a 100-dimensional vector, which can also be considered as a document representation. And for each, so this T here is topic, this word is word, this W is word. For each word also, you can consider that I have a distribution over belongingness over the different topics. This can also tell you give you a word vector. So in some sense, it connects with the SVD, because there also we had the different number of dimensions that we want to keep, and then here we have the terms, here we have the documents. So these vectors can be used analogously.
And sir, in the the algo that you have given on the left hand side, there you are considering theta1, theta2, theta3. That means we are considering there are 3 documents in this algo.
So this is about generating probability vectors using Dirichlet distribution. So theta1, theta2, theta3, that means we're assuming there are 3 topics. So I have 3 values here. So here we're generating the probability vector. We're generating the probability vector. And what is the probability vector? This theta t is one probability vector, where we say that, okay, for the current document, these are the belongingness to the different topics. So these 3 belongingness will be these 3 probability values. I mean, Si0, Si1, Si2. On the other hand, yeah.
Got it, sir. So, but sir, we just spoke about that theta d is basically the number of it is a distribution of the topics per document. So it's like doc topic. So the number of documents, those number of theta. So in a way, we'll get those many number of thetas as the output, right? So theta1, theta2, theta3 means 3 documents in that case, right?
Together, and we'll get a single theta matrix.
Yeah.
Matrix. This theta1 is a vector. Collection of theta t's will make a matrix that will get as output. And similarly, this will be invoked for the other side also. But here the number of dimensions will be equal to the number of. So if you remember, for each topic we are trying to identify the distribution of words.
Yeah.
Right? So there the number of dimensions in this vector will be equal to the number of words.
Got it, sir. Yeah.
Okay. So any further questions? If there is no, so just we say that SVD and this one, there is some connection. So just remember one thing, SVD in the matrix, right? In the matrix, the numbers can actually be anything. It can be positive, it can be negative, it can be very large. But here, due to the fact that, okay, each row here is a probability vector, and each row here also is a probability vector. So there is a very nice probabilistic interpretation to it. So the things will be, numbers will be small, is a probabilistic interpolation. That is one more reason people try to go ahead with this one. That LDA, that learning, which is sampling based procedure, takes a lot of time. But then, it's again here we are not trying to process one entire matrix altogether. So that is another consideration. Computation is large, but that kind of storage and other problems go away here. So LDA has become a de facto standard for topic modeling from large collections. So just to give you some examples, so there was one experiment that we were doing at one point of time. So where we took, we downloaded documents related to 20 or 25 different diseases from the internet. Okay, so one was asthma, then there was something like arthritis, there were IBS, and quite a few other things were there. So we, for 20 or 25 diseases, we downloaded a lot of documents, and these documents we then pre-processed and we fed to LDA, and the number of dimensions, because we knew what are the different diseases for, or the number of different diseases for which we had collected the document corpus, we set the number of topics accordingly. And then when we were looking at the LDA output, we saw that there is one cluster which talks about asthma. It's expected that we'll be finding asthma because we know that there are many documents belonging to that. Similarly for arthritis also we had, and so on. However, we got a few surprising clusters. So there was one cluster which talked about, say, lifestyle. There was one cluster which talks about problems which are mostly related to gynecology. But we never, when we started this process, have in our mind that when we have a collection like this, these can be, very important themes in this collection. So, I mean, this is where this kind of modeling actually is very helpful. There are topics which you expect and you will get, and there are topics which are surprising, but those are indeed present. Those things can also come out. So I didn't mention one thing, that for each document this topic vector will be there. It's easy to get. However, in the output, I mean, typically many times if you simply, when you run and the algorithm produces the output on the console, see, for each topic it cannot produce the vector for the probabilities for all the words, right? The number of words can be huge. So it typically produces the probabilities of the most probable words, the highest probability words for a document. And you can specify, say, 20 or 25 how many you want to print. And when you observe those words, most probable words for a topic, it actually gives you some idea regarding what this topic is possibly telling. So since this is not there, let me just pull it up from some web resource and show you to you.
So the time complexity of this would be very high, right? Because it is the total number of words in the document multiplied by the total number of documents, and then multiplied by the total number of topics.
Yeah, so it is a time complexity is high. However, when, I mean, it's not prohibitively high. So even for many large collections, when these algorithms are run, depending on the hardware configuration, the results actually comes fast only. Yeah. Okay, let me I mean, many different libraries, there are tools for visualizing the outputs as well. So okay, let me share a different screen and show you. I believe you can see the screen, topic modeling visualization.
Yes, sir.
Okay. So GenSim is a library which has topic modeling available as a function. So, and there are many such libraries. So here, okay, this is about yeah, importing things and so on. So data set, this is the data set that is being read and put into a data frame, and this tokenization, and then bigram trigram models, they have lemmatization they do, and this is the top model building part. So LDA model, the corpus you have to provide ID to word. There is a mapping from ID to word which created a dictionary, like to give index for each word, because we finally have the matrices, right? Word, topic, and topic. So this, for each word, what is the index that needs to be strictly maintained? Number of topics, some randomization state, and these are some other things. Now, I mean, this thing learns the topic modeling, and then if you print the topics, so that, as I said, this vectors will not have names. Sorry, these clusters will not have names, but we'll have some identifiers like 0, 1, 2, 3. So here, if you remember, we had num topics equal to 4. So 4, so there is 0, 1, 2, 3. And for topic 0, the word right, they got the highest probability. It got the high probability, 0.017. Topic people, 0.015. Organization, 0.014, and so on. So the top few it printed. So typically that is a configurable parameter in all these calls, how many we want to print. And then for topic 1, we have Christian, believe, God, state, Israel, and so on. Topic 2, American, bike, kill, year. So topic 3, team, game, hockey, play, NHL. So this is coming from the word topic vector. What is the document topic? So yeah, so here I think that directly is not mentioned, but for each topic, for each document, it is possible to get the, sorry for going back and forth. Yeah, for each document, you can identify the topic vector. I mean, that is also there as a field in that LDA model object. And here what they have shown from that, from those things, it also identifies the most dominant topic for each document. So these are the ones.
The keywords are the one which are words within a topic.
Yes.
Okay.
And this is the actual text. It gives an indication regarding why this topic became highly prominent in this document. So let me also add, let me also add this link. Slide. Okay.
So, one quick question. Like diagram that you have in PPT, which book are you following for this?
So this actually is covered from some other resources, not from specific book. So I think that also is a good point. So what could be a reference book for this one? So there is a book called Speech and Natural Language Processing. It is by Juravsky and Martin. Yeah, and this book is available as a free PDF from the authors only, so you can make use of it. Let me, I'll just,
That book contains has this topic like topic modeling and SVD, singular value decomposition.
yeah, I'll give you the links. It has the topic.
Okay, okay. So, can you just mention the headings like which because I like in
Well,
Trijit sir gave us the same book. I just went to the index once just to find out the topic that you have been covering. So
I
I'm
see.
not able to find that. So that's why I asked this.
Okay, let me also check that. So I just added a reference to yeah, so the first one is actually a hyperlink. So this one I just added, and now let me check the topic modeling topics in that book. Speech and natural. And for SVD, there is a book on information retrieval, which is by Manning and Raghavan. So let me just mention this in the chat window for the time being. For topic modeling, it's a large PDF. It is opening. I'll post it. I'll post it. Okay. So any further questions on this topic at this point? If not, then we can go for a 15 minutes break now. And when we come back, we'll continue our discussion on word representations.
Sure.
Sure. Sir, you were on mute actually.
Yeah, I'm opening the next set of slides. Yeah. Hmm. So
Hi, sir.
okay, yeah.
So, do we have last class Google Meet recordings? So, I didn't able to find it. Sorry.
Mm, it will be somewhere in the Google Meet. Yeah, I'll check the Google Drive. It should be there.
Okay. Please share via mail. Okay. Thanks.
Sir, can you share the PPT as well?
For the last class, just uploaded it. In the file section, it will be there. And today's one, after today's class, I'll upload. So if you go to file section, last lecture one part is there.
Okay, okay.
Okay. So till LDA, we saw the things. It's okay, and then we will look at some modern techniques for representing the words. And on the one of the very popular techniques was is word to vec. Now, so words as finally goal is to again get representations for words, and this technique was proposed in 2013. And before that, people were using many other techniques for different NLP tasks, and for very high level of understanding, high level of document understanding, like clustering, classification, with those kind of techniques, some reasonable to good accuracies people were getting. Then if we also look at some other tasks like name entity recognition, then parts of this tagging kind of things, where there is a structure in the language and that can be exploited. Even in those kinds of scenarios, good performances were being achieved, at least for English and other languages, based on the annotated corpora and so on, and the richness of the language, the morphological richness of the languages. I mean, performance guaranteed to a certain extent was possible. However, what was being observed is that all those performances were reaching a point, and beyond that, it was very difficult to get any further performance boost. In some sense, the performances were hitting a ceiling. There is no chance of going beyond. And then around this time, in 2013, this method came, and which changed that NLP landscape quite significantly. So here the assumption that they tried to make is that the any word, depending on what other words it co-occur with, based on that we can have a proper learning framework with specific objective functions, which can actually give us very good representations of the of the words. And then if you look at singular value decomposition, it's an unsupervised method. LDA, again an unsupervised method. Then there is probabilistic LSA. So PLSA is there, that is unsupervised. TF-IDF, there is no learning. So if we can impose some kind of learning while doing these vector representations, then it can actually guide that process somehow. However, problem is that getting annotated data becomes very difficult. So now they came up with a very interesting trick and very interesting technique, where they came up with some supervision which can be done in an automated way by looking at the document collection only. So this learning, coupled with the very useful and careful selection of objective functions, actually worked really well. And then the next 5-6 years, or even now, this is a very powerful technique for representing words. So their assumption is that the representation of a word is dictated by other surrounding words. So here we assume a fixed length context window. So suppose we have a window of 5 words where C is the central word that we are interested in, and there are 2 words after it, 2 words before it. So idea is that for each word which is appearing, or for each token which is, sorry, for each word which is appearing in the collection, we will have a vector representation, and at the very beginning we just initialize randomly. Then as the process goes on, so we will update the vector of a word by looking at what other words it is co-occurring with. We'll keep doing this process for each word, and then finally when this entire process converges, we can say that okay, our learning is complete and we can now use these word vectors for our tasks. So there are 2 different models that they proposed. One is the skip track model and the second one is continuous backup words model. So we were talking about supervision and objective, right? So this is how they construct the supervision sample. Suppose we have a sentence in our collection which says the algorithm's asymptotic complexity is quadratic. Okay? And each word in this sentence, in fact, each word in the collection, or say rather each token in the collection, will get a chance to dictate the learning process. How? Say, suppose this is the sentence currently under consideration, and for each sentence, each word also gets a look at. So suppose currently we're looking at this word called complexity. So what we do is we take the central word as complexity. We take 2 words before it. So algorithms is word -2, asymptotic is word -1. Word 1 is and word 2 is quadratic. Okay. Now this entire thing is there as our training example. Sorry, as our training instance. So here the window size is 5 tokens. Now by looking at this window, we define a learning task. So we want to predict the other words or the context words given the central or the target word. So here in this example, the central word or the target word is C, which is complexity, and W-2, W-1, W1, W2, these are the context word. We want the model to predict, given the central word or the target word, the other 4 words which are surrounding it. Okay, so can we come up with a model that will take the center word C as input and is able to produce these 4 words as the output? So this is called the skip trap model, and in the continuous bag of words model, again the same training sample, same sliding window will be there. However, the role of input and output will reverse from what we have seen in the previous slide. So here the context words will be provided as input. So W-2, W-1, W+1, W+2. These will be the inputs, and we have to predict the central or the target word. Now, again, if the model has learned well by looking at these context words, it should be expected to be able to predict the central word well. And if from a large collection, it is able to do this with a high accuracy, over a large number of tokens, we can say yes, the model has learned well. But again, remember that our goal was to get a vector representation for each word. So here in this process of predicting the output by looking into the input, this process should utilize and update the word vectors appropriately. Only then our purpose of word vector learning based on this setup becomes fulfilled. Okay, so any questions at this point? Okay, now let us see how So our goal is to, get this prediction. So given, for CBOW, so given these words, we try to predict the central word, or given the central word, we want to predict this. So in other words, we are given a context word, central word, and what words can appear in the context. They will be coming from the vocabulary only, right? So in this vocabulary space, if we are able to assign a probability to each of these words, each of the words in the vocabulary, we can hope that the probability for the words which are the correct in the context, right, their probabilities will be higher. That's what the expectation is. So based on this, we can actually come up with the objective function. So the objective function, the very first objective function looks like this. What does it tell? It says that you maximize the probability of seen word context pairs. Seen word context pairs means from the training data. So by looking at this, can anybody suggest this is the objective function for which model, skip tram or continuous backup words?
Continuous backup words.
Okay, and why?
Because there is a window of size C that we have set. To C, basically it's going from minus C to C for the current word, and
Therefore both, no? The text window, the sliding window part.
this there's a C.
Conditional probability is actually
Yeah,
that targeting. Target is actually given, so it's like
yeah,
given target. So that's why.
yeah. Given the center word, so we are predicting T plus J. J is spanning over minus C to C, so which is the context words. So,
Okay, so then it's a skip run.
Yeah. So these two models differ in only one scenario. Only one aspect. Input output. They are reversed. So in the continuous backup words, we give the context words, these multiple words as input, and one single word, which is the center word, we expect at the output. On the other hand, in skip tram, we give one single word, which is the center word as input, and surrounding words, these multiple words, we try to get at output. So here, since only one word WT is given, and this is in the outer summation. So once we fix this, these things actually vary based on the J value. So input remains 1, output changes from minus C to plus C. So this is actually the skip tram model. So what does the entire objective function mean? So forget the 1 by t part. It's for some averaging, it's clear. Now small t equal to 1 to capital T in this summation. So this means that in our entire collection, so if you look at any document, it will be having a sequence of words. Now each appearance of a word in a document is called a token, right? Or in other words, each appearance of a word in an entire collection is a token. So if the first document has n1 number of tokens, if the second document has n2 number of tokens, and so on. So the total number of tokens in that entire collection will be summation ni. Is there a question? Okay, so
Sir, what is the T value? Like T is 1 to T, small t is equal to 1 to T. So what is the capital T?
yeah, so that's what I'm explaining. So suppose you concatenate together all the documents. Okay, then you get a mega document. Now each appearance of a word in that mega document is a token in that collection, right? Now capital T is the number of such tokens. The first document has 10 tokens, second document is 20, third document is 30, and fourth document is 40 tokens. Then in this collection of 4 documents, we have total 100 tokens. Capital T is 100. Is that clear?
What is sir? Yeah.
So that is capital T. Now that means we give a chance to each token in the collection to be a center word. Okay. Now we have fixed one token as the center word. Now in that corresponding document, from that we can now have a sliding window, get the next two and previous two words as the uh, output targets, right? Now, so this is j from minus c to plus c. So this one will vary from t minus c to t plus c. In our example, our c value was 2. So t minus 2, t minus 1, t0, t1 and t2. So t0 thing we can ignore, and this is what the objective function is. So we are finally averaging over the number of tokens that we have in the collection. Now if there is any doubt regarding this objective function, yeah, please let me know.
Does capital T represent the vocabulary?
No. So when we say vocabulary, we talk about the unique words, right? Like a dictionary. However, here each appearance of a term is a separate token. Now in the sliding window, when we fix a document and keep sliding over, then it's possible that the same word comes as the center word from many places. So we'll consider each of them separately.
Okay, so it's not unique in that case, sir.
It's not unique. Repetitions we consider, because the context
Okay.
also changes there.
Okay, thank you.
Yeah. Anyone else with any other
So
question?
T is the number of all the words in the document, or just that word in number of that particular word in the document in a way?
Number of all appearances of all words together.
Okay.
And how do we find probability, sir? Like WT plus 1 given WT?
Yeah, we'll come to that. Yes, that will be the next thing that we discuss. So at this point, let us assume that there is a way to find this p. Now, under that assumption, I hope this objective function is clear. Now, as you mentioned, we need to identify a way to find this p. So here we assume that p is a probability where something given something is this conditional probability, right? Now this is given, we call it input or wi. This is the expected output, so w0, sorry, wo. Now here we want to utilize the vectors. Okay, so how do we utilize? So each word we say will have two different representations. Let me bring the pen. Yeah. Each word will have two different representations. This is output, this is input. Now each word will have a representation in the output and a different representation as the input. Okay, so now once we have the input word, we get the representation of that vector from this one. So it is called VWI, representation of the word from the input vector. And this one is the representation of the target from this output part. So we call it V prime WO. Now these two are vectors, so we can very easily take a dot product of them and we'll get a scalar. So this is nothing but the dot product. Okay, so what we do is we fix the input. Yes.
Sir, what is the vector representation here for this particular word? Is it a bag of words representation? What kind of representation is it?
So here we can assume that each vector will be, each word will be represented as a d-dimensional vector. Okay, so here in O and in I, if words are coming as rows, then each row has a d number of dimensions. Now we assume that these will be dense and compact vectors. So we initialize this entire WO and WI randomly. So it's not coming from TF-IDF. These are some vectors that this method will learn itself, starting from some random initialization.
I mean, suppose there is a one word, maybe just something called A, okay, or D. So how, suppose there are 10 words, and within that words, the D, how this word is particularly being represented, like all the elements being 0, and for that D word is going to be 1, or like, that is what I'm trying to understand how the vector representation will be actually.
So at the very beginning, we start with a random initialization of the vectors. Okay, so we know that we have these many words in the vocabulary. So for each word, so we create a matrix O of dimension V cross D, and we create another matrix I with a dimension of this. Then we can say now this matrix has to be initialized with something, because otherwise if it is not initialized, these operations we cannot do. How to initialize? We can simply very randomly initialize it. We can say that, okay, for each row it will be a say a normal, I mean each row will be normal, will be having a normal distribution. We can say, okay, each row will be a probability vector, whatever. So we start with a random initialization of the matrices O and I. And further, as we go along, this learning process will update these these matrices. At the end of the entire training process, when everything has converged, these vectors will be now more reliable, because they have seen the data and they have been manipulated by they have been manipulated with the goal of doing well in that task. Right now, this will become more meaningful, but start with a random initialization.
And how do we define, sir, this input and output? Because every word in the input output will also be in the input, right? Because we have same documents from which we created input and output.
See, okay, let me look here. So suppose this is one sentence that we have. So it says natural language processing and machine learning is fun and exciting. So we'll have a sliding window of size 5. So what we'll do is, the first word will give it a chance to be the center word. Now what we see is that before this there is nothing. So our left context will be blank. We can have special words or something to take to indicate blank words. And +1 and +2 are language and processing. So we'll run the algorithm once, run the model once, with input as natural and expected output as language and processing. So here W, then we slide again. We slide again, and now language becomes the center word, and the left context has one word now, one blank or unknown, and right context has processing and. So we have one more, and this comes as one more input to the model. Some algorithm predicts something and so on, and then next time this processing becomes a center word. Now what we want to do is, according to the objective function here, would like to predict what is the probability of and given language. We want to find the probability of machine given language, and similarly probability for no, I think here in this
It should be processing, right? Because processing is a center word right now.
You're right, yeah. So probability of and given processing, then probability of machine given processing. Now these two are taken care of, this one and this one. Now natural and language, we need to look at that. So probability of natural and then probability of language. Now these four probabilities, if we are able to find, then we are done with this inner summation part for this, right? Probability, if we are able to find, we can take a log of it, and here minus c2 plus c means minus 2 plus 2. So these four things come here, and when both these things are there, we can consider it as 1. There is no further update, or so that we can ignore. And this is for one specific token, which is processing. So this summation will be the contribution to the objective function by this sliding window, this instance. Is it clear?
Yes, sir. So my doubt was that are we doing one by one, like for each document, not for all at once in parallel?
Not one by one. So few such examples can be clubbed together and considered as a mini batch.
Okay.
So
In a
So
total
in that case, go ahead.
I think
Go
Sabir
ahead,
had
Aman.
go ahead, Abhishek. Go ahead, Abhishek.
Okay, so sir, if we like create a mini batch, now we had this input and output set, right? So now in this case, in output set, we'll have this three word, right? Like natural language and processing. And in the input set, all other words will go. Is this like that? So that we create the distance, that dot product and all. That was my doubt, that because we are taking one from the input and from the output set, and then we take the dot product between the two. So what is the input set and output set when we take the batch?
See, this processing becomes the input. These are the possible outputs. So it is one to many, right?
Okay.
One output, multiple outputs are there in this example. Now for now for this setup, one single training instance. Now for this, we want to compute this part, and then we'll get its contribution to this one.
Okay. Thank you, sir.
So in this case, what would be the example that you just gave, presented on that other slide?
Small t or
The capital T, the capital T.
capital T in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here capital T
Okay.
for this document, but there will be many. So this is only one sentence. There are many such documents, many such sentences. So what we hear is that the moment this small t changes, so this is small t equal to 0.
Mhm.
So this small t equal to 0, this small t equal, or say small t equal to 1, so t equal to 2, small t equal to 3. So that means each appearance of the word here is gives you one input output combination, right? So yeah, t equal to 0, natural is the center word. T equal to 1, language is the center word. T equal to through, processing. T equal to 3, 4, 5, 6, 7, 8. Now see that 8
Yeah.
we have and this and was there at small t equal to 3 also, but these two are different because here in this and we have is fun as the left context and exciting unknown as the right context. So is only from this. Now if you consider that we have a one mega document which is representative of the corpus where everything has been joined together. Actually we do not join together, but yeah, just for the counting says the continuity of counting. Yeah, so uh, each appearance of a term, each token which is there in this mega document, that gives us one value of small t. So the
Got it.
total number of tokens in that big document.
Okay. So irrespective of whether repetition or not, basically that just like here and is
Yes.
being repeated multiple times, but we're
Yes.
still considering 10 as the capital T.
Yeah.
Got it. So
However, please note that in the WO and WI matrix, so there we'll have one vector for each term from the vocabulary.
okay, without repetition in a way. Yeah.
Yes.
So what, okay, maybe we would be coming to that part, but what would be the O and WI for the word and in that case? Because then we have the repetition there, right?
It will have the same representation.
Okay, got it. Yeah.
Now, one thing is that, see, there is one word and it is appearing in many different contexts. So surroundings will change. And so sometimes, so suppose there is a word which is very topical in nature, say disease. Sometimes the disease will occur in with terms, say treatment. Sometimes it may occur with something like diagnosis. Sometimes it may also occur with things like diagnosis and other things. So, you know, as and when we look at all different contexts in which this word is appearing, we try to get a sense of the topic in which the word belongs, and that way the representation is actually directed towards that topic thing. So each appearance of the word will give one such training instance, and one this computation will happen for each such appearance. All right, now let me come back to the computation part. So in this example, when we fix our t equal to 3, we have these probabilities to be computed and then summed over, right? Now these are words, right? And process. So these are words, but how do we get the corresponding number so that we can compute something mathematically? So this is the input and this is the desired output, right? So essentially we'll get a representation of this. Now this representation we get from the matrix W(i), and this representation we get from the matrix W0. Okay, and to understand what is the value of probability and given, so this all should be given, and given processing, we will take the vector v prime for and vector v for processing from these two matrices, and we'll take a dot product of them. Okay, so that will give us some score for this one. It's not probability because it's just a dot product, and all these probabilities, I mean all possible probabilities will expect to sum to 1, but if you only leave at the dot product part, they will not sum to 1. So then we get the probability for this one, the second thing. Again, VWI we will get for processing, and vector for machine will get from the W0 matrix, and now that is our new V prime. Right? So like that we will do. So for a given V prime, so for language given processing, now this is coming as input, this is coming as input, sorry, this is coming as input and language was coming at output. So we will take vector for lang from W0 multiplied by vector for processing from Wi. These two vectors, they have the same dimension, so we can have a dot product among them. And keeping this one fixed, if we find this, if we change the words, suppose this is language and this is processing. So processing is given, but this output can be any of these, right? So we find the probabilities by changing all these possibilities. Now the probability of language given by processing will be like this one, which is this score divided by, I mean all other score, and then we raise to it. This is nothing but a softmax formulation. So if we consider this dot product as simple score, then given the input as fixed, the score for language is S0, sorry, S1. The score for some other word is S2.
So the capital W is the total number of tokens or number of words in that particular window?
Number of words in the vocabulary.
So that will be equal to T, right?
No, this capital T counts repetition. In V, we don't have repetitions.
Achha, capital T will have repetitions, but W will not be having. Yeah, okay.
That's correct. So if the same term appears again, we'll fetch the same entry from the matrix.
Okay, fine.
So,
But sir, for this input and output, we have to will we, if there is same word in input and output, will it have different representation once it learns, or it will have the same representation for one word? My question is that why do we have two different set, one for input and one for output?
so it will be two different words. Otherwise, W and WI, two different representations. Otherwise, W and WI will be the same if they contain same representation for each and every word. So
the embedding, learned embedding also will be the different for the same word for input and output.
Yes. So here the idea is that each word, when it is a center word, I mean, depending on the role, it assigns a different vector. So then people did many experiments. The properties of a word when it is coming from WO and when it is coming there as the center word, they're different. In fact, there were teams from Microsoft who did this experiment in around 2015 or around 15 with this. They saw that they used this for search query ranking, or sorry, document ranking in search. So there is a query, and for this query they found out the score for different documents and they did the ranking. So now query, from this query they get the vectors of the query words, and they did some example experiments with single word queries. So now for the query there is one representation, and then they find the similarity with document representations. Now there they said if you change the representations from WO to WI, you are getting different types of results. And in one case, I am unable to recall exactly whether the WO case or WI case. In one case, it was very topical results that they were getting. In the other case, it was not topical. It was a bit more diverse. So possibly when they used WI, they get the topical results. So there is change. So idea here is something like when a word is on its own, it has some representation, some property. On the other hand, when it is there in a group and trying to influence the representation of others, it has a different role.
Okay.
There are some experiments that people have done again with just similar to the experiment that I talked about, which is done by Microsoft. So in some cases, people then said, okay, let us just use WO plus WI by 2. So there are lots of works where people take the average. So to work with the representation of a word, they get its representation from the WO and from WI, and then they do the averaging.
Thank you, sir.
So fixing the context to processing, sorry, the center word to processing, we can actually find the scores for all different words from the vocabulary by just taking the dot product of the corresponding vectors. Now we are interested in probability, so this scores will map to the probability space by doing the softmax, right? So this is simply the approach. So now we are able to get the probability of this one, and once we are able to get the probability, this thing can be computed. Accordingly, we can optimize also. Now this was the first part, and then when people tried to put it into practice, they saw that if we only rely on the words which are there in context, and based on that if we do, instead of that, I mean, so instead of that, if we can also identify some kind of negative samples, okay, that okay, these two words appear together, so their affinity, their dot product and the subsequent probability will be high. Along with that, if we can contrast it with some other thing, like these two words, no, they cannot be in the in the window or in the context. If we are able to contrast among these two objectives, then the learning is better. So due to that, they added negative sampling also. So what happened is, for each word, say in case of processing, they also have, I mean, they sample a few negative examples. Okay, so the examples what we saw here are positive. So if we only rely on positive examples, I mean, we maybe the algorithm may increase the magnitude of all these vectors or other things, so that all these probabilities become very high, right? In fact, if the yeah, uh, in fact, we may also try to give the same representation to everybody, right? This objective will actually very high. But on the other hand, for words which are not in context, which are completely different, for them also this probability will actually, matching probability will be very high. So somehow that needs to be checked. So this contrasting actually helped there. So for each word, they identified some negative samples, and this negative sample identification also they tried various different strategies by looking at the frequency of each word. So we can say that, okay, for each word you get their frequencies, and those frequencies, that entire frequency pool, you can then convert to probabilities, and based on that probability you can add something as a negative example. So then people said, okay, instead of that, instead of the frequency f, you take f power alpha, where alpha is equal to 0.75, and many different mathematical functions for identifying the probability of picking a negative example that people took. So finally, but essentially the point is that these, we know these actual words from the context, they'll provide the positive examples. Then we'll have something as the negative examples. And here, this is also can be connected with the sigmoid function, or yeah. So we want this to be high, right? So that's why this is there, the positive. On the other hand, this we want to be low for the negative example. So that's why we have a negative here, and this together becomes the objective function. Okay, so I think there will be one example later on. I'll come to that. Now for skip drum, I mean, this formulation was for so we had one input. So this is 1 cross V. What does it mean? So we have one cell for each word from the vocabulary, and WT is a single word. So in this representation, WT's representation will have 1 in the corresponding position and 0 at everywhere else. So it becomes a 0 hot encoding for the word WT. Now from this WT, we need to get the representation for WI. Right? So this WI is nothing but W here. Now there are some changes in the terminologies going forward. So now if this one we multiply with the WV cross D, remember that, okay, there is one row for each word in the vocabulary and and each vector has dimension D. So this, if we multiply with W, it's very easy to see that we'll get the row which represents this word, right? So that is the D-dimensional representation. So 1 cross V multiplied by V cross D gives us 1 cross D. Now this one, we multiply this with W prime D cross V, isn't it? So that's what we were doing. This D-dimensional vector, we are taking the dot product with this one. So here we're doing the same thing. This D-dimensional vector, we are multiplying it with this one, and for 1 cross D multiplied by D cross V dimensions will give us 1 cross V. What is that? The scores for each word in the vocabulary. So when this thing got fixed, we got the bottleneck dimension also fixed, and this we are multiplying with this entire matrix, the transpose of this one. Now we get a single vector of dimension V, where the entry contained in each dimension is nothing but the score for that, the dot product. And these dot products we finally pass through a softmax layer to convert them to probabilities. Okay. And this is for the other thing, the continuous backup word. So there we have multiple things coming is input. So here we have one hot vector corresponding to each input token. So if the word is cat, so that cell has 1, everything else is 0. If w plus 1 is on, so that one cell has 1, everything else is 0. And these come here to the bottleneck layer. Okay, so this multiplied by w v cross n and this multiplied by w v cross n, we can sum them together. Okay, and this becomes this one, and this we multiplied with the other vector w prime. So and then we get a probability distribution over, I mean firstly score distribution over the all cardinality of v words. That score goes to probability space, and this is the target value. So here the target is set, and if we have the predicted probabilities and this is the actual probability, we can actually use a cross entropy kind of loss or any other loss to yeah, and then we can backpropagate that loss. So we need to finally learn these two matrices w and w prime. Is the input hidden layer? Yeah. So it's the score z and z2 y prime y hat we get. And suppose these are the different scores that we get from the method after the softmax, and this is the output. So we compute loss, we backpropagate. So this is one again from that example. When natural is 1, firstly we do a dot product of this one hot vector with the first matrix, right? And this dot product will do nothing but extract the row corresponding to that. So this becomes the hidden layer, and this hidden layer gets multiplied with the second matrix to get the scores z, to get the score z, and this a, yeah. Now this z to softmax, which is nothing but prediction. Yeah. So any doubts here? I believe if the yeah. So that is about the algorithm actually. So if there are any doubts, let me know.
Yeah. Sir, on the objective function slide, if you may please go once again. Yeah, the skip gram objective function. So here this summation at the very first step. Yeah, wt plus j given wt. So we in this objective function algorithm, you know, we heard that we are giving each token a chance to be a central token. So
Yeah.
this summation, is it taking into consideration only that one instance wherein one word is a token, or all the 10 instances where every word has been considered as a token? Is this summation considering all those instances?
Yeah, right.
Okay, yeah, because in the next slide, I think when you just shows the diagram pictorial representation, there that summation I could see just now. Some time back you shown that diagram. Yeah, this hidden layer. Sorry, just one slide before this. Sorry, one slide more where the diagram is there. Yeah, this hidden layer. This summation is happening. This is skip gram only, right, sir?
This is
This
continuous
is
of
this is
words.
continuous, yeah. So here that summation is visible because in hidden layer, you know, all the summations are being similarly skip gram also, right, sir? All the summations of
No, so this one is actually showing you the yeah. So this one is actually showing you the process for one instance. I mean one training instance.
but the algorithm, that summation is for all the instances, right? When every token is being word is considered as a central token.
Right, right. And in this kind of things, right? So when you know, if that is the objective function, then we need to be able to process that entire data. We need to be able to process that entire data, keep accumulating the probability values, and at the very end only we can do the summation and we can do one back propagation, right? So
Yeah.
but typically that will be too time consuming, and I think when we accumulate too many results, everything will get mixed. So although that is, you know, in some sense the objective that we want to achieve, but when we execute, we do not wait for that all those entirety to be covered. So in that connection, you can assume that yes, we have a small mini batch.
Okay. Got it. Yeah. Understood, sir.
Maybe
Sir,
coming from this, and here the capital T will be the number of tokens in this mini batch only.
got it. Got it. Sure, sir. Thanks. And sir, one more question. Connection to just now what you said. It appears, sir, that efficiency or accuracy will be more in CPOW because we are predicting only one and we have multiple words available. But computationally intensive, I think it looks that skipgram is better because we are just passing one and predicting many. Is that understanding right, sir, or is that a trade-off?
That's a good observation that in continuous backwards we have more on the input side. So it becomes, I mean, intuitively it becomes simpler to fill in the blank. At the same time, the output is large, output space is large for the skipgram. So that's why skipgram learning appears to be a bit more tougher than continuous backwards. However, thing is when there is a very large corpus, people have seen that the performance difference is not much. So if it's a small corpus, yes, what you said is fine, but large corpus, there is not much. That's why people study both actually.
Sir, I just didn't got clear because the number of parameters in both the skipgram or the continuous pack of words is just the same, right? So why the skipgram is performing better than the or is performing slower than the continuous pack of words?
Not slower as such. See, in one case you have many things
Mhm.
as coming as input and only one blank you have to fill. So intuitively that task is simpler as compared to the task where you have the only one word present and remaining four you have to predict.
Yeah, that is fine, but the weight updation and all those things, if we go mathematically, so can we derive it, or can we say it with a proof? Because mathematically it doesn't appear so, because the weight updation in both the type of structures will be just the same.
It will be same, but the thing is how well it can predict. So that will determine the loss value and the number of iterations taken to converge.
Okay. So the number of iterations in skipgram will be more, right? Okay.
I need to cross check. It appears so,
Uh-huh.
but yeah, we'll see if it has been documented anywhere by anybody.
Yeah. Also, can we compare the skipgram or the continuous pack of words? Apart from this, what feature does it has, or in which scenario we should go for continuous pack of words, or in which scenario skipgram is better?
Okay, so yeah, so I have not seen whether there is any study like that. There are some papers where people see that okay, the difference is not much, but the other things, what you have mentioned, maybe I need to see if there is any study which covers these aspects.
Okay, sir.
Sir, one doubt I also have on the network model page, if you can go there. So here there are two things. One is like your model weight, and another is the input vector. We need to also learn the input vector itself, right? And
No, so
I'm not
there's
sure whether.
nothing but one hot. So this is one hot representation. It will not be learned.
So,
It is
but
just
the embedding, we are learning embedding, right? Because initially we started with the random embedding.
yeah. So these embeddings are there in W and W prime. This is nothing
Oh,
but
so
W by
embedding itself is the weight of the network.
yes, and these are learned.
Oh, okay, understood. Thank you.
And sir, one thing on the embedding. So, like most of the vector DBs, they have their own intrinsic embedding. So basically, for us, let's say if I take an example of any vector DB, say Chroma DB. So Chroma vector DB has its own embedding. Then basically we are just simply passing our inputs to that vector DB and using the vector DB directly here in that case.
So I am not much familiar with the vector DB and how exactly things are stored. I don't know. Will it if it allows that okay? I learn my word vectors using some algorithms, and those will be inside the vector DB. Or when we initialize a vector DB, is there a way in which we can say that okay, you learn the vectors using this method? So that part I'm not very clear about.
Okay.
Okay, so this was about word2vec, which was and which is actually quite popular nowadays, even when we talk about different other kinds of models. In many scenarios, the very first thing that we feed to the different models will be the word2vec representations. In fact, as we said, depending on the entire corpus, we can get the word2vec representations. So what people had done, in fact, that is one more benefit that the NLP community saw, is that these word2vec examples, or these word2vec vectors that we learned, uh, again, these computations, it is not possible for a small organization to do. So it requires a lots of computations, and there are many organizations which ran word2vec on large collections of data, and those vectors they released, right? So these are the pre-trained vectors. So take a large corpus, you learn this representations by considering skip RAM or continuous backup or whatever, and what vectors you get, what vectors they got, they released it. Then since these are trained on very large volume of data, we can say somewhat confidently that the representations which are learned, the representations which the words have, they are representative of the word's real world meaning, because it is coming from huge corpora. So if that is the case, then when a small organization is trying to develop an algorithm for a small use case for which a lot of data, annotated data, is not there, but still, since these vectors now are expected to represent real world knowledge, so they can actually be used directly, and the base level performance of the algorithms can actually be quite higher as compared to the scenario where we started with random vectors or some other assumption like TF, IDF, and whatever. So this also started an era, or and a phase where this pre-training and pre-trained vectors, that concept started becoming very popular. Okay, now around half an hour we have, so let us move on to the next technique here. So there are some references, I'll share the slides. Okay, now before we go there, this word2vec, it became popular due to many reasons. Firstly, this kind of distributed representation, a word getting its representation depending on the large number of contexts it comes, so that gave a very generic, not I won't say generic, a very confident vector representations for the different words. That was one thing. So, and the second thing was this pre-training, this became possible, and pre-training and release of the vectors which become possible. And the third thing is that there are some other interesting properties that people observed in this. So one was word analogy. So suppose we look at the vectors that we have for man, woman, uncle, aunt, king, queen. So if man, the vector is this, for woman the vector is this, for uncle the vector is this, for aunt the vector is this. They saw that the translation that you need to apply to the vector for man to reach the vector for woman, the same translation you can apply to the vector of uncle to reach the vector of aunt, and so on. Now when I say same, it's not exactly same, it won't be possible, but yeah, it's very similar to the push that you need here, the translation that you need here to reach here, right? Now they saw that this thing happens for many different pairs, many different types of pairs, and that was really surprising and at the same time convincing that these vectors mean something. So another thing that they saw is that if you have the here the male female that gender pairs were there, and then they also had something like country and capital. For different countries they listed the vectors, for different for their capitals they also listed the vectors, and they saw that the difference between the vectors of a country and the corresponding capital, this is also very similar. And there was something for superlative also, say small, smaller, smallest, large, larger, largest, quite, quieter, quietest. Here also, if you look at these three, so there also, the translations were actually very similar. So in other words, these models were able to find some kind of analogies. So this something, so this was an interesting observation. Now for evaluating word analogy, for evaluating the quality of embeddings, so it can be done in many different ways. So what we said is that given a corpora, we can learn the word vectors by following an algorithm like this. However, uh, one may say that, okay, I have my own algorithm and it is better than word to vec. How do we judge, right? How do we measure which algorithm is better? Okay, so there are many different techniques which were proposed. One thing could be like very simple. For each word you get the vectors and then you identify a downstream task. It can be say document clustering. So input is a document or say sentence. We want to say classification. Okay, we want to identify its case, like whether it is coming from technology or sports or politics and whatever. So to construct the input representation, you make use of the word to vec representations. So for each constituent word, we get to word to vec, and then you apply something so that from this multitude of vectors, we get one single vector representing the document, and then pass it to some classification algorithm. And if there are n number of different word representation techniques, identify which technique is leading to the best performance for that classification task. So this is one. Now this is called extrinsic evaluation. You need an additional data to find the quality of the word representation schemes, right? Now,
Can you just repeat it? Extreme key, uh, the class name.
extrinsic classification.
Acha,
So we require some external data, and
yes.
from that external data is actually dictating. Now there can be different things. Somebody may say that okay, the algorithm that you have applied, it's not very powerful, so that even if the uh, input embeddings are very different or they're very powerful, this algorithm somehow is not able to make a full utilization of that, because we know that different classification algorithms also, they may have their own, yeah, so we evaluate different algorithms also, right? So that is one thing. The other thing was like, can we have some kind of intrinsic evaluation where we do not have to rely on any additional task or task specific data? And people used word analogies as one kind of intrinsic mechanisms for evaluating word embedding techniques. So how does it work? So they say that word analogy task is something like A is to B equals C is to what? So we specify three things as input A, B, and C, and we want to predict this question mark. So this A and B could be like man and woman, and C could be uncle. Or A and B could be like China and Beijing, and C could be Russia. So can you suggest any ideas regarding how this word analogy task can be solved? You can refer to this. Suppose this is A.
So I think we will find the orientation between, for example, men and women, and we'll apply the same orientation on the another variable corresponding to which we would like to find.
Okay, then can you, and whatever you have said, can you translate into some mathematical steps so that the machine can perform these exact same thing? For example, when you say reorientation, how
Yeah.
can we find that the exact mathematical steps?
I think we can find the cosine similarity.
Okay.
It
Okay.
will be
Any
C minus A plus B. D should be C minus A plus B.
we
Or
know E, right?
Yeah, D.
I think that we
So
want to find out. So how do
yeah,
we get?
so D should be C minus A minus B in the bracket. So that is C minus A plus B.
So how do you tell algorithm that D should be this?
The vector
We
space
know
distance
A
basically.
and C.
We can find
Yes.
translation and rotation matrix and apply the same translation and rotation on C.
Yeah.
Say again. Apply some translation and rotation. What translation? What rotation?
So like when man goes to woman, what's the translation from A to B, and what's the rotation from A to B? If we have that as a matrix representation, then we apply this matrix to the C, and then we can reach to D.
Anyone else who can clearly spell out the steps? You can make use of whatever you see on this slide as hint.
So the cosine distance between the two. So basically,
I think
cos. Sorry, go ahead. Ravitha.
yeah, I think they are simply algebraic statement like uncle minus man will become a vector, and that vector can be added to woman minus man. Then you arrive at the aunt.
Okay, let me tell you the exact steps which an algorithm can execute for this task. So step one, we have A, B, C are given and D we have to find out. So step one, you find the translation T, which is given by T equal to B minus A. Okay, so this gives you this matrix. So this vector difference itself will have some magnitude and some orientation, some direction. So no need to further in
Yes.
specific orientation again. Next, this T we apply to C. That means we compute C plus T, and let us call this new vector as X. X equal to C plus T. Now the C plus T may not actually go to this unt vector. No, there can be many other vectors here. Right? Next, with T, you do a nearest neighbor search with this X. So this nearest neighbor search is done on this entire. You can have a dictionary or collection of vectors or whatever, where for each word from the vocabulary you have that representations. So this is something like the WI matrix. So each word has a representation there. Now you feed X as a query vector and identify the top K from here. And you can say the one which is at the top is your prediction for D.
So can you repeat, please? It's not clear the third point. How you are able to determine the direction of D? That's
Sir, you are on mute.
So this is a list of k vectors, and we want to find d there. And based on this, we will judge what is the quality of this algorithm. Now, can you suggest any metric that can capture this notion, whether in the k results which are thrown by this algorithm, we are expecting to find d? And whether this d is present here or where it is present, accordingly will determine which algorithm is best. Can you suggest a metric for this purpose?
Are you looking for like the metric means the arithmetic
Evaluation metric.
Like
Evaluation.
Euclidean distance or
Also the argmax of the cosine distance, the cosine vector, and we can do the argmax on that, the cosine distance.
Say again.
So the argmax basically will go with the maximization of basically the cosine distance.
Between what and what?
So it would be basically so in a way the if we go with the vector of king minus the vector of man plus vector of woman, and we take the
wait a minute. So I think there was a period where I got disconnected. So I'm not sure whether it was clear to you. So 1, 2, 3, these are the steps, and at the end of step 3 we get a collection of vectors S, which is k vectors, and yeah, so these are the algorithm suggestion regarding what could be the which could be like D, right? And your algorithm suggests you k different outputs, say 1, 2, k, and these k things are in a list S, and we want to find our target D there. Now, based on these two things, can you suggest an evaluation metric that can be used to judge the performance of this algorithm?
Oh, okay. I think I got disconnected then. Yeah. It would be the min of Euclidean distance between the D and the F. In that case, the elements in the F.
Okay. So this is one min over all case distance of D.
Yeah, D and
SK. Okay. Anyone else?
We can also use the cosine similarity instead of Euclidean in the same formula.
Delta will become cosine. In that case, it will be maximum.
Yeah, correct.
Okay. Any other thing? Okay, so some other techniques could be like simply like hit rate. Is this D present in this S or not? Okay, if it is present, reward 1. If it is not there, score is 0. You sum it over. I mean, that's the performance. And for if there are many different analogy tasks, you sum it over all those performances. Another thing could be like so this hit rate is nothing like recall. Another thing could be like a mean reciprocal rank kind of thing. So you identify the position I where this thing is present. Okay. So and the score is 1 by I. So if you see that okay, this D is present at the very first place, then the score is 1. Then if it is present in the second position, the score is 1 by 2. If it is present in the third position, it is 1 by 3. If it is not present, the score is 0. So like that also, it is called reciprocal rank. It's reciprocal or inverse of the rank at which this thing is present. Okay, so this can be one more approach. So when people propose word to embed, word to vec, sorry, when people propose word embeddings, especially this kind of embeddings, then this analogy task is used as a very uh, popular intrinsic evaluation metric. But as we all know, we are dealing with large number of vectors, very large vector space and so on. So this exact thing will never happen. This exact thing will never, this equality will never happen. We can possibly say, okay, almost equal or something. So that's why exact match will not possibly get, but we can have a reasonable sized k, and as long as we find our the expected result d in this k, we should be good enough. And the other things that you have suggested, even those are good techniques for evaluating. Yes.
How are we going to decide the K?
That will be there for any such. You can have different things like k equal to 5, 10, 15, 20.
So the less the value of K would be, the better the algorithm can be considered, right?
Right. We are becoming more strict there. Yeah. Okay, so then just one thing, one last point to mention here is that this technique, this representation is it gives one single representation for each word, irrespective of where it is appearing. Right? So in this matrix w prime, which are being learned, so here the number of rows is equal to the number of elements in the vocabulary, right? So irrespective of where, I mean, although when we are doing the training, each different occurrence of the same word we are considering differently, but then when we are doing the modifications here, these modifications go to the same vector. So that means if you consider a word which is appearing in many different contexts with many different meanings, but this method will give exactly same representation to the word each and every time. So if you consider the word like uh, set the temperature to high versus A is a set of elements, or I bought a set of two trousers. In each of these cases, the word set is used in many different contexts, but when we try to extract the embedding for the word set, we'll extract it from this W only, and every time we'll get one single vector. So in that way, it is a non-contextual vector representation. The representation of the word, does the final representation that is there does not depend on the context in which it is appearing. So it's a non-contextual algorithm or representation. So then there were many such modifications to word to vec. It became so popular, people were and then we also did some work where we say that word to vec is only based on co-occurrence and sliding window. But what if, and it says that okay, the words which are related, which actually mention okay, this is the context, sorry, this is the meaning which it will try to capture. So all these are coming through co-occurrence, but sometimes the exact clue may lie beyond the context window also. So we'll talk about parsing, dependency parsing later. So what if those related words are actually outside the context window? So can we include some signals from dependency parsing? Then we also have some other linguistic resources like WordNet, which have been developed by humans, who are experts in linguistics and so on. So can we use those kind of things also? So where it says, okay, these two are synonyms, these two are antonyms, this word expands into this and so on. Or this is a, say, animal and dog, there is a relation, specialization and generalization. Can we make use of these kinds of things to make the representations better? So we had all these pairs, right? Target and context. So probability of target word given context word. So can we add some more examples by looking at word name, dependency parsing and so on, and then we learn the representations. So there are techniques like that also. Okay, so all right. Okay, so that's all that we can cover today. I think newer topic will need more time. So if there are any questions, you may please ask. Otherwise, we can conclude the session here today.
So, matlab, will we cover this hierarchical softmax because as part of the word to it?
No, will not cover. There is a possibly there is a hyperlink that I have given, but no, will not cover it.
Okay. So, how many quizzes will be there in the school?
Some 3-4 we are planning.
And number of assignments?
That we are yet to decide whether we will go with the assignment route or a project. That to be decided.
Okay. Yeah.
So the topics the topics that we are going to cover, you showed in the at the beginning of the slide. Are all they will be covered by you, or does Srijit sir that he is going to?
Yes, this we together will cover all this.
Okay.
Okay then. Thanks for joining. So we'll conclude to this class here. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.